Hello, welcome to my video series of algorithms. This is part 4 of Module 2, Logic and Proof. In this video, we will discuss logical equivalence. In the previous video, we introduced logical connectives, which allow us to construct compound statements with more sophisticated meanings. Some compound statements, however, can be too complicated to understand when being translated into human language. For example, consider a compound statement, not P, or not Q. We define the statement P as the prices are high, and Q as the wages are increasing. If we directly translate it into human language, it would be, it is not that prices are not high or wages are not increasing. You can see that this sentence is difficult to understand. It would take us a while to figure out whether the prices and the wages are increasing. Therefore, it would be nice if there's a way that allows us to simplify such a complex statement without changing its original meaning. To achieve this goal, we introduced the notion of logical equivalence. In its high-level definition, we say two statements bear logical equivalence if they express the same meaning. In this case, when we have a proof or argument, we can first identify a complex statement from it, replace it with a logically equivalent simpler statement, and make the entire proof easier to understand. Recall that we have two types of statements. The first type includes statements that do not involve quantifiers. We call these statements regular statements. The second type includes statements that involve quantifiers. We call these statements quantified predicates. The notions of logical equivalence defined for the two types of statements are similar, but a bit different. Therefore, we'll discuss them separately. To denote logical equivalence, we use the symbol equivalent, which contains three horizontal bars. For example, we can denote P is logically equivalent to Q in this way. The notation applies to both regular statements and quantified predicates. Let's begin with discussing logical equivalence for regular statements. We say two regular statements are logically equivalent if, for any combination of the truth values of their elementary statements, the truth values for both statements are identical. We can show the logical equivalence between two regular statements using a truth table, just like what we did in the previous video. Below, we'll give two examples. First, we want to show that not P or Q is logically equivalent to not P and not Q. This is also called the De Morgan law. Note that there are two elementary statements involved. They are P and Q. Therefore, we will need 4 rows to enumerate all their truth value combinations. We fill up these two columns by enumerating all truth values combinations for P and Q. We then add the auxiliary columns to store the intermediate and final results. After that, we can fill up the truth table using the truth value determination rules introduced in the previous video. For example, we can fill up the second and the third columns, not P and not Q, by referring to the truth values of P and Q, respectively, and apply the truth value determination rules of the negation connective. We can repeat the same process to fill up the rest of the columns. Finally, we can compare the truth values of the columns representing the two statements of interest, and confirm that they have identical values in each row. Now, we can claim that the two statements are logically equivalent. Let's look at the second example. Determine whether P implies Q is logically equivalent to not P implies not Q. We can do the same thing to construct and fill up the truth table. Note that When comparing the truth values of the two statements of interest, we can see two rows have different truth values. It means that these two statements are not logically equivalent. Using the above process, people have proven the logical equivalences between many statements. These pre-proven logical equivalences are summarized into a set of laws, which can help us simplify complex arguments or proofs. Below, we will list a set of common logical equivalence laws. Note that the list is by no means exhaustive. We will not discuss each one of them in detail, as it is more of the topic of discrete math. You can pause the video to see each one of them. You are also encouraged to study the corresponding material in discrete math if interested. First, we have the commutative laws, associative laws, and distributive laws. Second, we have the identity laws, negation laws, and double negation laws. Note that here we use T to denote tautology, which is always true. Here we also use C to denote contradiction, which is always false. Then we have the idempotent laws, universal bound laws, and De Morgan laws. Finally, the absorption laws and the negations of tautology and contradiction. In reality, we can repeatedly use these pre-proven laws to simplify a complex statement. The process is similar to simplifying an algebraic formula. Here, logical equivalence for statements can be viewed as quantitative equality for formulae. Now, let's take a look at a real example. Define P as I am 40 years old and Q as I enjoy ice creams. We want to express the statement not P or not P and Q in English and simplify the statement if necessary. Here is the direct translation of the statement. It is not that either I am 40 years old or that I am not 40 years old and I enjoy ice cream. It sounds awkward, and we would like to simplify it using logical equivalence. We can simplify the statement using a set of logical equivalence laws. The process is similar to simplifying an algebraic expression. Eventually, we can simplify the original statement into not P and not Q, which is in a much shorter form. We can then translate the simplified statement into English. Now, we have the statement saying, I am not 40 years old and I don't enjoy ice creams. This expression is much clearer compared to the original expression. Now, let's move on to discuss the logical equivalence of quantified predicates. The definition here is very similar to that for regular statements. However, there are indeed some differences such that we need to investigate logical equivalence of quantified predicates using a bit different approach. We'll discuss in detail below. Let's look at the definition first. Two quantified predicates are logically equivalent if and only if they have the same truth value no matter which combination of values is substituted into the variables of these statements, and which domain of closure is used for the parameters. You can see that the definition is very similar to that for regular statements. However, for the quantified predicates, we need to enumerate all combinations of values in the domains. In this case, can we also use a truth table to prove the logical equivalence of quantified predicates? Recall how we use truth tables to prove the logical equivalence for regular statements. We first enumerate all combinations of the truth values for the elementary statements, then fill up the table and compare the truth values of the statements of interest one by one. Imagine what would happen if we simply extend this approach to quantified predicates. With the truth table, we need to enumerate all combinations of elements in the domains. To determine whether the two quantified predicates shown here are equivalent, we need to enumerate and examine all cases where px and qx take the element x0, x1, all the way through xn. Now, we can easily see that the choose table needs to have n rows, as n is the size of the domain. In reality, some domains can be very large, and some can be infinite, such as the set of real numbers. Therefore, while it is not wrong in theory to use a truth table to show logical equivalence for quantified predicates, it is infeasible in practice. Therefore, we will have to prove or argue the logical equivalence for quantified predicates. To facilitate the construction of the proof, we will need to introduce some additional information to better understand this definition. First, note that a quantified predicate can be transformed into a set of regular statements. The possibility stems from the fact that both quantified predicates and regular statements are genuine statements and have unambiguous truth values. For an existential statement, exists xpx, it is equivalent to px0 or px1 or px2 all the way through pxn, where the union of x0, x1 all the way through xn is the domain of X. To see the equivalence, recall that an existential statement says one element in the domain can make the predicate true. Therefore, it is equivalent to the disjunction of the predicates with all possible elements or values in the domain. Similarly, for a universal statement for all xpx, it is equivalent to px0 and px1 and px2 all the way through pxn, where the union of x0, x1 all the way through xn is the domain of X. Recall that a universal statement says all elements in the domain can make the predicate true. Therefore, it is equivalent to the conjunction of the predicates with all possible elements or values in the domain. Based on the above information, we can further make inferences regarding existential and universal statements. First, let's look at existential statements. If xc is in the domain D and pxc is true, then, based on definition we know, the existential statement exists xpx is true. This is called existential generalization. On the other hand, if we know an existential statement exists xpx is true, then there exists xc in the domain D that can make pxc true. This is called existential instantiation. We can make similar inferences for universal statements as well. If an arbitrary element xc in the domain D can make pxc true, then, based on definition, we know that the universal statement for all xpx is true. This is called universal generalization. On the other hand, if we know a universal statement for all xpx is true, then an arbitrary element xc in the domain D can make pxc true. This is called universal instantiation. Note that we use xc to represent an element when discussing both existential and universal statements above. However, xc could mean different things. When discussing existential statements, xc is a specific element that we don't know. That is, we know it exists, but we do not have sufficient information to identify it from the domain. On the other hand, when discussing universal statements, xc is an arbitrary element from the domain. That is, every element in the domain can serve as xc. Now, let's look at two examples of proving logical equivalence for quantified predicates. First, show that for all x, px and qx is equivalent to for all xpx and for all xqx. To show their equivalence, we need to show if one statement is true, then the other one is true, and vice versa. In other words, we need to show that the double implication relation between the two statements is true. This is because both logical equivalence and double implication require that the two statements have identical truth values for all scenarios. In this case, we need to show that if for all x, px, and qx is true, then for all x, px, and for all x, qx is true. We also need to show that if for all x, px, and for all x, qx is true, then for all x, px, and qx is true. Let's first prove that if for all x, px, and qx is true, then for all x, px, and for all x, qx is true. If for all x, px, and qx is true, by universal instantiation, we know that for any arbitrary element xc in the domain, pxc and qxc is true. It further means that pxc is true and qxc is true for any arbitrary element xc. Then, by universal generalization, we can say that for all x, px is true and for all x, qx is true. Next, we need to show that if for all x, px, and for all x, qx is true, then for all x, px, and qx is true. If for all x, px, and for all x, qx is true, then we know for all x, px is true and for all x, qx is true. Using universal instantiation, we know for any arbitrary element xc in the domain, pxc is true and qxc is true. In other words, pxc and qxc is true for any arbitrary element xc. Then, by universal generalization, we know that for all x, px, and qx is true. Taken together, we have proven for all x, px, and qx is equivalent to for all x, px, and for all x, qx. Let's look at the second example. Show that not for all x, px is equivalent to exists x, not px. This is also called De Morgan law with quantified predicates. Similar to the previous example, the proof should contain two parts. First, we need to show that if not for all x, px is true, then exists x, not px is true. Second, we need to show if exists x, not px is true, then not for all x, px is true. Let's start with proving if not for all x, px is true, then exists x, not px is true. If not for all x, px is true, then we know it is not true that pxc is true for any arbitrary element xc in the domain. In other words, there exists some element xc that must make pxc false, or make not pxc true. Then, using existential generalization, we know exists x, not pxc is true. Next, let's prove that if exists x, not px is true, then not for all x, px is true. If exists x, not px is true, then using existential instantiation, we know that there exists some xc in the domain that makes not pxc true. It means that pxc is false. When pxc is false, it further makes px0 and px1 and all the way through pxn false. This is because xc is in the domain. Now, by definition, we know for all x, px is false. Then its negation, not for all x, px, is true. Taken together, we have proven that not for all x px is equivalent to exists x, not px. Similar to regular statements, there also exists a list of pre-proven logical equivalence laws for quantified predicates. And we can also use them to simplify quantified predicates in the same way as regular statements. Further, when a complex statement contains both regular statements and quantified predicates, we can use laws for both types together for simplification. If interested, you can find more examples and exercises from discrete math materials. In summary, we have discussed the basic notion of logical equivalence. We say two statements have the same truth values under all scenarios. We have discussed how to prove logical equivalence for regular statements and quantified predicates, respectively. Some pre-proven logical equivalence laws exist, and we can use them to simplify complex statements when constructing proofs or arguments. Thank you for watching, and see you next time.